So this section is on related rates. Basically, these are going to be all word problems where two things or more are happening at the same time with relation to time. We're going to heavily use implicit differentiation here. And the best way to learn related rates is just to do a bunch of examples because they turn up in a lot of different ways. So let's start with a fairly typical example of a ladder sliding. So we saw an example of this already, but in this case, when we did the example before about a ladder sliding, we were just looking at how fast that angle changed with respect to a distance, and we weren't taking into account time. This time we're going to be taking into account time. So let's start with a 10-meter long ladder. Lies against a wall or the side of a building. So it begins sliding. It's sliding on the wall with the bottom moving away from the wall. And the rate that this is moving away from the wall is 2 meters per second. Okay, so a 10-meter long ladder lies against the side of a building. It begins sliding down the wall with the bottom moving away from the bottom of the wall at 2 meters per second. When the bottom of the ladder is 6 meters from the wall, how fast is the top of the ladder moving down the wall? So there's going to be a couple of things we almost always want to do when we start our related rates problems. And the first one is usually going to be we want to draw a picture of what's going on. So suppose here is our side of our building, here's the ground. We can go ahead and make our ladder going across here. So this is 10 meters long. We know what's happening is this bottom is moving in this direction, so this is moving in this direction. Okay. Now let's go ahead and label. We have two things that are changing here as this moves along. We have this part down here is changing. So as the ladder moves down, X is getting bigger. As the ladder moves down, Y is getting smaller. And what we're given in the problem is the bottom of the ladder is moving away from the wall at 2 meters per second. So that means dx dt is equal to 2 meters per second. Okay, and so what do we want to find? That's another thing we're going to want to list. We're going to want to list what we know and what we want to find. So we want to find dy dt when x is equal to 6. So it's good to write down what we're trying to find so that we can make sure, because some of the problems will be kind of complicated, and it's good to have written down what you're looking for. So what other information do we know? Well, we know the ladder here makes a triangle, so we can use Pythagorean theorem to say 10 squared is equal to x squared plus y squared. And this is going to be the main equation we use. So we can differentiate this equation, and we're going to differentiate with respect to t. So even though t doesn't seem to show up in the picture, we know we have dx dt and we want dy dt. So we're going to differentiate this equation with respect to t. So that's going to make us use implicit differentiation. So when I differentiate 10 squared, I just get 0 because that's a constant. And now I'm going to get a 2x, but then I get a dx dt with that because I've differentiated with respect to t. And then same thing, I get a 2y, but then I put a dy dt with that because I've differentiated with respect to t again. So now remember, we're trying to find dy dt, so we're going to solve for that. So we this equation, and we isolate. I'm going to have y dy dt is equal to negative x dx dt. Notice we've canceled out that 2. So that means dy dt is given by negative x over y dx dt. So now we want to look at this and say, okay, what do we know? I know what this value is, and I know I want this when x is equal to 6. So I know what this value is. It's this one down here that I don't know yet. Otherwise, I could just plug everything in. But we can use that equation for the Pythagorean theorem where I had 10 squared is equal to x squared plus y squared. So when x is equal to 6, I get 100 is equal to 6 squared plus y squared. So I can subtract that and say y squared is equal to 64, which implies y is equal to 8, because we know that y has to be positive here. So that allows me to plug everything back in then, and I have dy dt is equal to negative 6 over 8. And then remember, our dx dt was given by 2 meters per second, so this is times 2. So this becomes a negative 6 over 4, which is negative 3/2. And remember, this is in meters per second. And one thing to note here is we have a negative sign, which makes sense because if we recall from the beginning of the problem, I said as the ladder slides down, y is getting smaller. So the change in y with respect to t should be negative because y is getting smaller as we go. So that's where that negative sign is coming from there. Okay, so that's a fairly simple one to start with. Really, you'll see what we're going to see when we're doing these related rates problems is setting up the picture, labeling it, and then doing this thing where we figure out, write down what do we know, what do we want to know. That's usually the hard part. Actually doing the calculus and taking the derivatives is actually the easy part of this process. Okay, so let's try some more examples of this. Okay, so we have a cylindrical tank with radius 2 meters, and it's filling with water at 3 meters cubed per minute. And we want to know how fast is the height of the water in the tank changing. So let's start with a picture. So I have a cylindrical tank here like this. Okay, and so we know the radius here is 2 meters. And then I know that my volume, dV dt, so if V is volume, this is changing with 3 meters cubed per minute. And so then what I'm looking for here is when I have this, say this is the level of the water, so let's call the level of the water H. So we want to know dH dt when H is equal to 2. Oh wait, no, sorry. We don't have any H there. We just want to know dH dt. 2 is the radius of the tank. Okay. So we don't actually need to know what H is for this. So the other thing we have is the volume of a cylinder is given by pi r squared H. So I'll expect you to know simple formulas like this one. if it's something complicated like a cone or something like that, I'll give you those formulas. Okay, so what we can say then is I want to differentiate this with respect to t. Notice that the radius is not changing with respect to t, so r is constant with respect to t. We know that r is always equal to 2 here. It doesn't change. So I can write that formula as v is equal to pi 2 squared h. So this is 4 pi h. And now we differentiate this with respect to t, so dv dt is going to be 4 pi, and then I'm just going to get a dh dt. So I'm looking for dh dt, so I just write this as 1 over 4 pi, and I have dv dt. And notice dv dt was 3, so this is 3 over 4 pi. And then note the 4 here had units of meters squared, so this is, meters squared. And so this is 3 over 4 pi meters per minute. Remember, units at the top divided by units at the bottom, so units of h are meters, and we're taking our time to be in terms of minutes. Okay, so let's try one that's a little bit more complicated, working our way up. Okay, so we have a spotlight on the ground. It's shining on a wall 12 meters away. A 2-meter tall person is walking from the spotlight towards the wall at 1.6 meters per second. We want to know how fast is the length of the shadow on the wall changing when the person is 4 meters from the wall. So let's go ahead and start drawing our pictures here and figuring out what we're trying to find. So let's go ahead and say here is our wall. Okay. And we'll say over here, this is our spotlight. So spotlight is shining in this direction like this. And so this is, if you have our person here that's 2 meters tall, this spotlight here is shining like this and is casting a shadow here. So spotlight goes like this, it casts a shadow. So this part is our shadow. And so I can say, I know this entire distance here is 12. Let's call this distance from here to here, let's call this x. So then this distance from here to here is 12 minus x. And we'll call the height of the shadow here, we'll call this h. Okay. So I know the person is moving towards the wall at 1.6 meters per second. So that means dx dt, remember the x is getting smaller here, so this is negative 1.6 meters per second. Okay. And we want dH dt when x is equal to 4. Right? Because that's when the person will be 2 meters or 4 meters from the wall. So what we can do here is we can use something called similar triangles, and the similar triangles is going to show up quite a bit. So I have a triangle here, and then I have the entire triangle. So we use the ratio of those sides. So I have the smaller triangle has height 2 and base 12 minus x. And by similar triangle, since this is inside of this, this will be h over the entire distance 12. So this is similar triangles. So if you don't remember similar triangles, what similar triangles says is if I have a triangle kind of inside another triangle, and this is A and this is B, and this entire distance here is C, and this is D, then A over B is the same thing as C over D. So that's from like high school geometry classes usually where you learn that, but in case you didn't remember it, there it is. We're going to use it pretty often. So remember, we're looking for dH dt, so let's solve this thing for h. So h is equal to 24 over 12 minus x. And now we can differentiate this, so the left-hand side will just be dH dt, that's nice and easy. The right-hand side we're going to have to use, you could use quotient rule, I'll just use, I'll view this as 24 times 12 minus x to the negative 1 and use chain rule. So this will become minus 24 over 12 minus x squared, because we subtract 1 from the numerator, or the power, and then I have the derivative inside, which is minus 1, and then I need a dx dt because I'm differentiating with respect to t. Yes. Okay. So that looks good. So this becomes 24 over 12 minus x squared dx dt. Okay, so now we want this when x is equal to 4. So we plug that in. I have 24 over 12 minus 4 squared, and then I have the minus 1.6 for the dx dt. So this gives me 24 over 8 squared times negative 1.6, and this is in meters per second. Okay, so that's what that's changing. The rate that that's changing at, you can write this as negative 24 1.6 over 8 squared, and you can simplify this some if you like, but it's fine to leave it like that. Okay, let's go ahead and do one in groups now. Okay, so we have a square that's where the sides are increasing at 3 centimeters per second. You want to know what is the rate of the area of the square increasing when the area of the square is 16 centimeters cubed. So I'll give you some time to work on this. Okay, so let's go ahead and go over this now. So let's draw our picture here. So let's say it's a square, so it has the same side length. We know dx dt is given by 3 centimeters per second. And we want to know how much the area is increasing. So we want dA dt when a is equal to 16. So note that a is given by x squared. So this would be also same way, in other words, when x is equal to 4. So we'll take this equation here for a and differentiate it. So I'll get dA dt is equal to 2x dx dt. And now we can just plug in those values. So I have 2, and then my x should be 4, and my dx dt is 3. So this is 24. And what are our units? Well, units of area are centimeters squared, and units of time was seconds. Okay, so let's try another example now. Okay, so we have two ships. They're 100 kilometers, ship A is 100 kilometers west of ship B. Ship A is sailing south at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Okay, so this is a little bit more complicated than what we've had. So let's put ship A right here. Ship A is sailing south. We'll put ship B up here somewhere. We don't want to put them directly next to each other because they have had some, they're going to be moving from times. We do know this distance here, going straight across, this is 100 kilometers. Okay. And what we're interested in is this distance here. If I call this h, we want dh dt. Well, when t is equal to 4, because it's 4 hours later because we want it at 4 p.m. Okay, let's maybe not call it h. Let's call it L for like I'd like to use D, but we don't want to use D as well, so we use L for length here. Okay, and so we can go ahead. One thing we could do is we can kind of make a little triangle with this, like this, and we can call it, say, this side here Y. And then we know this part here is 100, so we'll end up with a triangle here. So notice using that triangle, I have L squared is equal to 100 squared plus Y squared. So I can differentiate this now. So I'm going to have 2L dL dt is equal to 2Y dy dt. And so what we want to know here is, well, I need to know L, Y, and dy dt. So notice, since ship A is going this direction and it's going 35 kilometers per hour, and this is 25 kilometers per hour, y itself is changing at the sum of those. So dy dt is changing at 25 plus 35 kilometers per hour. So this is 60 kilometers per hour. And then we want to figure out, well, what is y when t is equal to 4? So after 4 hours, well, ship A has traveled 4 times 35 kilometers, which is 140 kilometers, ship A, and ship B has traveled 4 times 24 kilometers, which is 100 kilometers. So at 4 p.m., y is going to be the sum of these two, so 140 plus 100, which is 240 kilometers. So now if I solve for dl dt, I can go ahead and cancel those 2's, and I will have dl dt is equal to y over L dy dt. And I know what y is, I know what dy dt is, and then I can get the L here from the Pythagorean equation here. That will give me what my L is. So I have dl dt is equal to my y, which is 240, over square root of 100 squared plus 240 squared. And then my dy dt, which was 60. And this whole answer is in kilometers per hour. So as you see, just as I said, setting up the problem and drawing the pictures, getting everything labeled is usually the hardest part of it. All right, so getting this picture figured out, what we know, what we don't know, that's often the hardest part of dealing with these problems. Okay, so we have an inverted conical tank. Water is leaking out of it at a rate of 10,000 centimeters cubed per minute, and at the same time, we're pumping water into the tank at a constant rate. The tank has height 600 centimeters, and diameter of the tank at the top is 400 centimeters. If the water level is rising at 20 centimeters per minute when the height of the water is 200 centimeters, find the rate the water is being pumped into the tank. Okay, there's a lot going on this one. So let's go ahead and start with a picture here and some equations that we need. So like I said, I don't expect you to know the volume of a cone off the top of your head, but this is given by pi over 3 r squared h if r and h are the height and radius of the cone. So if this is r and this is h, then this is the volume for a cone. Okay, so for our particular cone, we know the diameter here is 400 at the top, so I can say from here to here, this is 200. And I know the height here, we said the height is 600 centimeters. But now we're gonna be pumping some water into this. So we have here that there's some water level here, and let's call this little r and this little h. Now we're going to say the water is entering at some constant rate. So we want to figure that out. So let's let A be the rate the water enters the tank. Okay, so water's flowing in at A meters cubed per minute, or centimeters cubed per minute. And we know it's going out at 10,000 centimeters cubed per minute. So if we think of the volume here is the volume of water, that volume would be given by pi over 3 r squared h. And the change in the volume for this amount, well, this is the rate in minus the rate out. And so the rate in, we know, is A, and the rate out is 10,000. And this is in centimeters cubed per minute. On the other hand, we also can use this equation here for V to get dV dt. So dV dt, if I use that equation, now that little r and the little h are both changing, so I'm going to have to use product rule here. So I'm going to get a 2rh dr dt plus r squared dh dt. Okay, so now we have to figure out these values here. So which ones do I know? Well, we're given, we want the water level, if the water level is rising at 20 centimeters per minute, when the height is 200, so I know that the height, dh dt, I know that's given by 20 when h is equal to 200. So I need to find dr dt, and I need to find r. So what I'm going to do is I'm going to look at this cone from the side here. Yes. And now I can use similar triangles again. So I know that this is 400. I know that the total height is 600. So if I make triangles here like this, we can say just these triangles over here on the side. So this is 200. This is r. This is h, and the whole thing is 600. So I have r over h is the same as 200 over 600, which is 1/3. So r is equal to 1/3 h. So that means I can figure out when h is equal to 200, then r is equal to 200 over 3. And I can also take the derivative to get dr dt is equal to 1/3 dh dt. And now I have everything I need to be able to plug in. So I have dv dt, and so I'm going to have here, just plugging into this equation at the top, I have my pi over 3, 2, and then I'm going to have my 200 over 3, and then I've got my h, which is 200, and then my dr dt, which is 1/3 dh dt, which is 20, and then plus, so this is big brackets here, and now I have r squared, so this is 200 over 3 squared, and then dh dt, which is 20. So that gives me my dv dt. And so now all I do is I go back up to the other version, which I said was dv dt is a minus 10,000, and I solve this for a. So a is equal to dv dt plus 10,000, which is this mess that we just found here. So 2 times 200 over 3 times 200 times 20 over 3 plus 200 over 3 squared times 20. And that gives me my oh, and then I need plus 10,000. And remember, this is in centimeters cubed per minute. Okay, so let's go ahead and try another one in groups now. And you can, of course, simplify that answer if you like and get an approximation with a decimal. But we don't need to do that. We can leave it as the exact answer. Okay, so we have a street light mounted on top of a 12-foot pole, a 5-foot tall person. So G, let's fix that. And the person is 40 feet from the pole. Okay, so let's start that over again. A streetlight is mounted on top of a 12-foot pole. A 5-foot tall person walks away from the pole at 2 feet per second along a straight path. How fast is the tip of the shadow moving when this person is 40 feet from the pole? Okay, so go ahead and take some time to work on that, and we'll come back in a few minutes. Okay, let's go ahead and go through this. So one thing to be careful of is notice what we're asking for here is tip of the shadow. It's different than the length of the shadow. So that's something that can trip you up on this. So let's draw our pole here. So we have our light up here shining down. So this is 12. Our person is standing here like this, 5, and then we draw the shadow there. Okay, so what we have, if I label this part as X and this part as Y, notice Y is the length of the shadow. But the tip of the shadow is X plus Y distance. So what we actually want is we want d dt of X plus Y. Just for how fast the tip of the shadow is moving. Now, if we wanted length of the shadow, we would have wanted dy dt, but that wasn't what we were asked, so be careful there. It's a little confusing. Different textbooks will ask you different ways, so we're just being precise and following the tip of the shadow here. So notice what we know is I know dx dt is equal to 2 feet per second. Okay. And now I can use similar triangles. I need to figure out dt of x plus y. So I can use similar triangles and I can write x plus y over 12 is the same thing as y over 5. Now go ahead and multiply both sides by 12 and then both sides by 5. I'm going to get 5x plus y is 12y, which gives me 5x plus 5y is equal to 12y. Subtract the y's, I'm going to get 5x is equal to 7y, or y is equal to 5/7 x. Now when I look at d dt of x plus y, I can write this as d dt of x plus 5/7 x, which is d dt, and notice this will become 12/7 x. Bring that 12 over 7 out front, and I just have dx dt left over, which we said was 2. So this is 24/7 feet per second. So that's it for related rates. Most of the tricks that you'll need on homework problems and stuff follow some of the tricks we've used here. In particular, the similar triangles we've used here comes up quite often.